I'd like to introduce you to the data set that we'll be using for most of the tutorials, as well as discuss indexing time points and frequency points and electrodes in Matlab. This is a very important bit of code that you will need to learn, and it's very important, but it's also deceptively simple, and so therefore easy to make mistakes. So the data set that we will be using is the sample data that comes with the book. You can download it from my website. The data come in EEG Lab format. You don't need EEG Lab to import or to view the data. You can also use any other format that you want for the code that we'll be using for the rest of the tutorial. Field trip format is fine, any other format is fine, but then you will have to convert it to EEG Lab format or change the code a bit. I happen to like the way that EEG Lab formats the data, so that's why I have some preference for keeping my data in this format. So the data are stored as a structure called EEG, and you can see there are many fields in this EEG structure. I will highlight some of the most important ones. Perhaps the most important field is this data field, so EEG.data. This is a 64 by 640 by 99 matrix, so it's a cube of data. And the organization of the dimensions are channels, 64 channels, and then time, 640 time points, and 99 is trials. And you can see these numbers also reflected here in number of channels, 64, number of time points, 640, also the number of elements in EEG.times, which is the vector of times in milliseconds. We'll talk about that in a minute. 99 trials, you can see EEG.trials. Another important field of this structure is called chanlogs. And you can see this has 64 elements corresponding to 64 channels. And as we'll see in a minute, this contains the channel location information for each of the channels that you have data for. Okay, so let's talk about indexing. Here is the problem that we want to solve. We want to create a topographical plot of the trial average activity at 300 milliseconds. And so you might define some variable to be the time point that you want in milliseconds, and then you average the data from, here you can see EEG.data from all channels, all electrodes, from this time point, and from all the trials, and then we take the mean or the average over the third dimension, which is trials. And so data to plot, therefore, oops, sorry, I have to run that line first. Data to plot, therefore, becomes a channel vector. And so this is the thing that we want to plot. So we can run this code, and this looks nice. We see a topographical plot, but there might be a problem. We look up here and we see from the title that this is a topo plot from 168 milliseconds. And so this is suspicious. Something weird is happening because we specified that we want 300 milliseconds, but when we wrote the title of this plot, it turned out to be 168 milliseconds. And the problem here, as you might already guess, is that this number 300 is being used as an index. And so this is the 300th time point, not time point 300 milliseconds. So how do we figure out which index, which time point actually corresponds to 300 milliseconds? So we can do it this way. We can plot EEG.times. And you can see these are the indices. So it goes up to 640. We have 640 time points. And these are the times in milliseconds. So this is stimulus onset, the beginning of the trial, time 0, and 1 second after the trial onset. So we can, for example, take this plotting tool and search around for 300 milliseconds. Okay, and we're about there. So now we know that the 334th time point is 300 milliseconds. or close to 300 milliseconds. In fact, we don't have exactly 300 milliseconds in here, in part because the sampling rate is not some multiple of or fraction of kilohertz that would give us exactly 300 milliseconds. So you can imagine that this procedure works, but it's a bit tedious and it's not really scalable if you need to extract a large number, dozens or maybe hundreds of time points. So we want to be able to automate this procedure somehow. So here's what we're going to do. Instead of plotting EEG.times, we are going to plot EEG.times minus the time point that we want to identify. So now you can see that actually just shifted this line on the y-axis. We didn't really do much else. But we've changed the problem slightly now, because now instead of trying to find the point closest to 300, we want to find the time point that's closest to 0, right? Because we've subtracted off the time point that we want. So how can we find the point that's closest to 0 in this function? One way to do it is by taking the absolute value of this function. And now you just see the distance of each, or the time at each point away from 0, where 0 is actually 300, or the point closest to 300. So now this is a simple problem. We just want to find the smallest value in this function. And so for that, we can use the function min. And this tells us 0.7813, but this is not a sensible number because it's not an index. There's no 0.7813th element in EEG.times. So in fact, what we want here is not the first output of min, but the second output of min. And the second output is now going to tell us where we found the minimum. And that gives us 334. So now we know that EEG.times min IDX is the time point that is closest to 300 milliseconds. And now you can see this minimum value is actually just the offset, the error, the distance between the actual time that was closest to what we wanted and what we actually wanted. So now what we really want to do is copy this line into here. So now we are not getting the 300th time point, but the time index that corresponds to 300 milliseconds. So now I'm just going to paste that indexing variable in here. And now we can produce another topographical plot, and this looks much better. The time point is also accurate. Okay, so this min ABS construction is a very general construction that you can use for many different types of variables, of different information. For example, here is an illustration applying the same concept, but now to a vector of frequencies. So now this you'll see when we start doing the Fourier transform or wavelet convolution. We get a vector of frequencies, and this will be in hertz. So this is going to be 42 linearly spaced frequencies between 2 hertz and 100 hertz. And let's say we want to analyze data at 23 hertz. So as you can imagine, if you just take the 23rd element of frex, this variable frex, it is not 23 hertz. It is in fact 54 hertz. So we use the same procedure here, min ABS, and then frex this variable of, in this case, it's not time points, but frequencies in hertz. And this is the frequency that we want. And now we see that the index is 10. So this means that the 10th element in this vector frex is as close as we're going to get to 23 hertz. So now this can get a bit confusing because you have to know that this value corresponds to hertz and this value corresponds to indices. So the way I help myself remember this is by always using the letters IDX for index when I'm creating a variable that corresponds to an index. So this helps keep things clear in my mind. Okay, so just so you know, you can also use this function dsearchn and that will give you the same result as this min ABS construction. dsearchn is a more general formula. It works for multi-dimensional spaces. If you are searching for the closest point in a three-dimensional space to some XYZ coordinates, for example, dsearchn will work for that. I like to use min ABS, particularly when teaching, just because I find it very intuitive to understand how this construction works, whereas this is just a Matlab function that's designed for slightly more complicated situations. Okay, so now we know how to index time and frequency, and now we need to do the same thing for electrodes. And here the issue is, let's say you want to get the data from electrode P1, but we don't know a priori, or we shouldn't have to know a priori, which channel, which numbered channel in the data set corresponds to P1. So is P1 the first channel in the data set, or the 10th channel, or the 35th channel? We need a way to figure this out. And so the way we figure this out is by using a function called string compare. And the I here at the end means to ignore the case. So that means we can do P1 with a lowercase or P1 with an uppercase, and we will get the same result. So what we are going to do with this function is match this electrode name to a cell array of all the electrode names that we have in the data. So you can see this is eeg.chandlokes.labels. And these are all the text labels of the electrodes that are given in the imported data file, which were specified by the EEG equipment manufacturer. So we run this line, and we see that the result seems to be lots of zeros, 64 zeros in fact, and only one 1. In fact, these are not really zeros and ones, although they look like zeros and ones. These are really Boolean true-false variables. So this is false, 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 and then we have a true value here. So this means that this one value, this is where the electrode name matches the electrode labels. So we can test this to be sure. We can say eeg.chandlokes at this electrode index. And here we are using MATLAB's logical indexing option to return one value where this function was true. And now we see indeed the label is P1, and then these are all the position coordinates that topographical mapping will rely on. So now we can plot an ERP from this electrode that we specify here by taking the EEG.data, and we say we want the data from this electrode, all time points, all trials, and then we take the mean over the third dimension, which is trials, and we plot that against time. So now we have this event-related potential from electrode P1. Okay, so now imagine we want multiple electrodes, in this case 3. So this might be the case if we are averaging the data from multiple electrodes together, or extracting data from these 3 electrodes for subsequent analyses. So now we have this array of electrode labels that we want, P1, FC6, and T18. And now here we are going to initialize the indices. So now these are all zeros, but we want to populate this vector with numbers. So the number of the electrode that corresponds to P1 and FC6 and T18. All right, so here we have a loop that goes over channels. And I can already tell you that this loop has 3 mistakes in it. And so if you are up for a challenge, I would encourage you to pause the video here and see if you can identify and fix the 3 errors. So, or you can just keep watching and be lazy, and I will do it for you. So when I have a loop that I'm not sure if it works, or if I just wrote a loop for the first time, what I like to do is not run the entire loop, but instead run through the loop one line at a time to see what everything does and make sure that everything works. So this is, of course, a very simple case where the entire loop is only one line, but very often you'll see larger loops with tens or maybe even hundreds of lines of code. Okay, so we are going to just assign this looping index variable to 1. I always have my looping index variables have a variable name that ends with I. And this is useful because then anytime I'm inside the loop, I know that chan I corresponds to the looping index for a loop over channels. So we start at 1, we go to length of electrode names, which is 3, so that makes sense. It's good to do a lot of sanity checks here. And now let's try to run this line. Okay, so we get an error, and the error message says something about size. So the first thing you should do when you see an error message related to size is look at the sizes of the different variables. We know that it's happening somewhere in this string compare function. So it's happening somewhere in here. There's only 2 inputs. So something is wrong with the size of this or with the size of this. This we saw earlier. So this is 64. And now here, the previous time when we ran this line of code string compare, we only had one element in here. So now let's have this also loop over frequency such that at each, over channels such that at each iteration within this loop, we're only going to be doing string compare for one channel. Okay, oops, that's supposed to be Jenny. All right, and now it works. It does not produce an error, so that's good. So now let's try running the whole line. Oh, and now we get another error. Now it's AI equals B. The number of elements in B and I must be the same. So again, we see the error message is something about the number of elements, something about the sizes. So the first thing we should do is look at the sizes of these different matrices. So this is size something about equal. So we want to see what the size is on the left of the equal sign and on the right of the equal sign. So Matlab is expecting this to be a 1-by-1 matrix, which is a scalar, so just a single number. Okay, so now let's see how that compares to the size of this. And this is a 1-by-64 matrix, so this is an array. And this is not going to fit inside of a scalar. So what we need to do is, rather than have this whole logical index, we just find the one single element in here that is non-zero. And this we can do using the function find. So now we see that the 20th element is non-zero. So let's put find in here like this. And now we run this and it works. And we can look at the value of electrode IDX and we can see it's 2000. So we only got through the first iteration. And so this is to be expected. Now what we want to do is run this entire loop and populate the rest of this variable. So let's try that. Okay, and now we get the third error. So now let's see which iteration. It was on the third iteration when it crashed. So now let's see what happens here. Okay, so we have an empty matrix. This is empty because it's trying to find the electrode called T18. But in fact, there is no electrode called T18 because this was just a typo on my behalf. So we can go back and change this. If you want to make this code a little bit more user-friendly, you can do something like try to run this, and then if that doesn't work, then catch me, which is actually Matlab error, not just catch me, although it is poetic. And then we can say error, something wrong with electrode labeling. Okay, so now if we would run this again, we would get this error message. So, but we've fixed that up here. And now what we can do is plot all of these ERPs simultaneously from all three of these electrodes. And here I just put a legend on there so we can coordinate the labels of the electrodes with the colors. So we can see, for example, that the parietal electrode gives the strongest response here.